Human life is built on observing periodic natural cycles. We track our existence through the repeating rhythm of shadows moving across the Earth. We eventually translated these cycles into mechanical gears, creating devices that divide the day into uniform, predictable units to coordinate our societies. In the practice of modern physics, time is defined operationally as what a clock reads. It is a numerical value used to measure change, motion, and the sequence of events. This reliance on measurement supports the Newtonian view of the universe. In this classical model, time is an absolute background, a kind of universal clock flowing at the same rate for everyone, everywhere. This perspective matches our daily intuition perfectly. It creates the sense of a shared objective now that links every point in the universe together in a single moment. However, this intuition of a universal, uniform flow is a localized experience that fails when looking at the mechanics of the wider cosmos. Trusting our everyday perception of time obscures a reality that is far more complex and observer-dependent than our mechanical clocks suggest. Albert Einstein challenged the Newtonian assumption of a universal background, arguing that time could not be separated from the observer. He introduced the paradigm of spacetime, where time is permanently fused with the three dimensions of space into a single flexible fabric. Because of this fusion, time is subject to dilation. As this diagram shows, gravity and velocity change the rate at which time passes. A clock positioned deep within a gravitational field ticks slower than one floating in the void of deep space. This physical discrepancy in clock speeds eliminates the possibility of universal simultaneity. Events that appear to happen at the same time for one observer will occur at different moments for another, depending on their motion and their proximity to mass. There is no privileged frame of reference in the universe that can claim to represent the one true present moment. The passage of time is a localized, relative phenomenon dictated by an observer's specific state of motion and the surrounding gravitational field. While Einstein's equations require time to be flexible, quantum mechanics treats time as a simple, continuous parameter that does not warp or bend. Reconciling these two incompatible versions of time is the central hurdle for any unified theory of reality. If physics cannot provide a single definition of now, we must consider alternative frameworks, like the relationalist view. Aristotle defined time not as a thing that exists on its own, but as a measure of change, a way for the mind to order events. This leads to the block universe theory. In this model, time is a static dimension where every moment is already laid out. Within this block, the past, present, and future are all equally real and exist simultaneously as fixed coordinates in a four-dimensional geometry. If the universe is a static block, our perception of time flowing from one second to the next is likely a construct of human consciousness rather than a physical reality. We live within a paradox. Time is the essential engine of causality and motion, yet its fundamental nature is still contested by our best theories. Human perception of time is often subjective, shifting with our attention and memory, but that doesn't change its status as a measurable physical quantity. Despite the lack of a universal clock, the standardization of localized time remains the only way we can organize our world or track the evolution of the stars. Time is the scale we use to chart the cosmos, even as its fundamental nature remains an open question.